Hey everyone. So when we left off before spring break, we was looking at the Claissen condensation reaction. So I'm gonna go ahead and just go over the Claissen condensation again. I think we got par way through it, but I didn't work some examples, so I'm just gonna go over it one more time. And so the Claissen condensation reaction, just like the aldol type reaction, but it takes place between two ester molecules. So let's go ahead and look at example. Okay, so if I have two ester molecules, so in the aldol reaction, we took off that alpha proton, so we had a base present. We have our alpha protons here. And so that base can take off an alpha proton. Just like with the aldol reaction, we saw, okay, so that makes a nucleophile, so a second molecule can now behave as the electrophile. So remember the carbonyl, polar covalent bond, so the electrons are pulled closer to the oxygen, making a partial positive of that carbon. So I have a second molecule, okay, and so it'll react with itself, attach the carbonyl, make an O minus. So at this point, if it was a typical aldol reaction, we'd protonate here and make the OH group, or you could undergo condensation where you form your double bond there, so you end up with your alpha beta unsaturated ketone. But when you have an ester, instead of becoming protonated, since you have this ester group that's a good leaving group, what you see happen is it reforms the double bond and kicks off your ester as your leaving group. And so you end up with that molecule, beta keto ester. So if I was just drawing out this one, I didn't want to go through the whole mechanism. I just wanted to draw the product of that reaction. I draw out one of my ester molecules. And at the alpha position, I'm going to take off one of my hydrogens and show something connected to it. So I took off the alpha proton. Now what I'm going to show it connected to is the carbonyl minus the second molecule, carbonyl, the second molecule, minus that OET, the ester group there. And so that'd be the product of that reaction, which in this case ends up being the acetoacetic ester. Reaction of two different esters is termed a mixed Claissen reaction. Mixed Claissen reactions are successful only when one of the two ester components has no alpha hydrogens. Just like when we went over the aldol reaction, where if you had a source of alpha protons in each compound and they're equally acidic, you're going to get 4 different products. And so for mixed Claissen reactions to be successful, one must not have any alpha protons. So let's look at the product of this reaction. And so I only have one source of alpha protons here. Okay, so I only have one source of alpha protons there, and so that's alpha protons that I'll remove. So I'm going to show that one bonded. So here's my ester. There's no alpha protons here, and so I'm going to attach that carbonyl and kick off that leaving group. So what I have attached to alpha position would be just that carbonyl. If I looked at this problem here, it says, what product would you obtain from Claissen condensation of ethyl propanoate? So first I have to be able to draw ethyl propanoate. So propanoate is, prop is 3 carbons. I know it's an ester, okay? So I have an ester functionality. And so 3 carbons, C double bond O, CH2, CH3. So then I have ethyl in front of the entire name. That means the ethyl group's attached to the oxygen of my ester. So I'm going to draw the product of this reaction now. So I'm going to draw this, and I'm going to kind of reverse the order here. Where there is my alpha proton. Okay, here's the carbon with the alpha proton attached to it. So here's my alpha proton. So I take off one of those hydrogens, and I'm going to show something connected to it. Now what else do I have attached? I still have this CH3 attached. So I'm going to attach that as well. So now I've got my first molecule drawn. Now I'm going to attach it to my second molecule. So it's going to attach to the C double bond O. I'm going to lose the ethoxy group here. So it'll be C double bond O, CH2, CH3. So that'd be the product of that reaction. If I look at the next problem, it says diethyl oxalate can give high yields in mixed Claissen reactions. What product would you expect to obtain from reaction of ethyl acetate with diethyl oxalate? So ethyl acetate, so acetate is indicating this group, so it's an ester. Ethyl acetate, so I have an ethyl group attached to the oxygen. Diethyl oxalate so I'm given the structure of that one. And so, go ahead and move it down here so you can see it all. So I'm reacting those together. So again, I'm going to take my ester here. So remember, ET stands for an ethyl group, so that's CH3CH2. And so then that's attached to C double bond O. Here's my alpha position. That's what I'm going to show connected to something. So CH2, I'm showing that to form a bond. Now here, I'm going to attach it to a carbonyl and kick off an ethoxy leaving group. So if I do that, I'd have C double bond O, C double bond O, OET. So there's not any alpha protons here, so I don't have to worry about it reacting with itself or any alpha protons being removed from this compound. So this mixed Claissen reaction would be successful. Dieckmann cyclization is a Claissen reaction that involves the cyclization of a compound. Just like with the intermolecular aldol reactions, the Dieckmann cyclization favors the formation of 5 or 6 membered rings. let's look at an example. So to see a Dieckmann cyclization, see if it'll work to form the right, see if it will undergo intermolecular Claissen reaction. You go from an alpha position, so I'm going to pick out one of the alpha positions on either side. So here's the alpha position. So you always go from your alpha position to your carbonyl. So I'll say 1, so here's 1, 2, 3, 4, 5. So going from the alpha position to another carbonyl can form a 5-membered ring. So that's what would happen. So it would form, attach to that carbonyl, and then it would reform the carbonyl and kick off my ester. But what I'm going to do is form a 5-membered ring. So I'm going to go over here and draw a 5-membered ring. Label it 1, 2, 3, 4, 5. And so at 1, I have this ester group. And then 2 is just a CH2, 3 is a CH2, 4 is a CH2, then 5, that's where I have my carbonyl reform. And so that'd be the structure of the compound that I would get there. The product of a Dieckmann cyclization can be further alkylated and decarboxylated by a series of reactions similar to the acetoacetic ester synthesis. Let's go ahead and look at that. And so one way that we've looked at to add alkyl groups is to either use LDA if you only have a monocarbonyl compound. If you have a dicarbonyl compound, you can just use sodium ethoxide. And so here I have an alpha proton in between 2 carbonyls, so that's going to make it more acidic since it's in between 2 carbonyls. The formyl antion can be stabilized through resonance. So I can add some kind of alkyl group, just like the acetoacetic ester synthesis, where you used your base to remove the proton in between the 2 carbonyls, reacted with an alkyl halide. It added to that position in place of your alpha proton. And just like with the acetoacetic ester synthesis and malonic ester synthesis, we can hydrolyze that with H3O+. Okay, so that becomes an OH group. And so then I have a carboxylic acid that's 2 atoms away from another carbonyl. So if I heat that up under decarboxylation, and I'll lose that as carbon dioxide. So I can get rid of that ester group that way. Let's go ahead and look at a problem in your textbook. So if we look at 23-11. So to show the products you would expect to obtain by Claissen condensation of the following esters. So this is 23-11. So I have, let's just draw this out, CH3, CH3. So I have two CH3s attached to the CH, and I have a CH2. Now, master, I want to draw the Claissen condensation product of that reaction. So here's my alpha proton. So that's why I'm going to show connected to my second molecule. So I'm going to start off with my ester there, the ETO. So here's my alpha position. I'm going to show that connected to another molecule. So what else do I have attached though? I have this isopropyl group here. So I'm going to show it still being attached there. So here's this molecule, the first molecule, and I have showing a bond from the alpha position. So it attaches to the carbonyl of a second molecule. I'm going to keep that carbonyl since it's an ester because it will reform the carbonyl and kick off the ethoxy group. So then I still have CH2 and the isopropyl group attached. And I've showed the CH3s attached here, one to the side, one to the bottom here, one on top, one to the bottom. It's the exact same thing. You'd also draw that out and just say CH, put parentheses and put CH3 and the 2 outside the parentheses. That'd be the same thing as well. Let's go ahead and look at another problem. Look at 23-14. So what product would you expect from the following reaction? So I have a diester here. So, and it's symmetric. So I have CH2, CH2, CH3, CH2, CH2. So going from the other direction is the exact same thing. If it was not the exact same thing, I'd have to take the alpha position from one side and go to the other carbonyl and do the same thing from the other side. So I'm going to say 1, 2, 3, 4, 5, 6. So I go from the alpha position from one carbonyl to the carbonyl of the second functional group on the molecule. So alpha position of the first functional group, the first ester functional group, to the carbonyl of the second ester functional group. And I count out 6, so I know it forms a 6-membered ring. Okay. So 1, I still have this ester attached. So 1, I still have the ester attached. 3, I have a methyl group, so I'm going to come over here to 3 and add a methyl group. 4, 5, 6 is my carbonyl. So 6 is my carbonyl. You can leave the numbers on there you want to, or you can just draw out the numbers. So there's the molecule that would be formed. Let's go ahead and look at the next one. Dieckmann cyclization of diethyl 3-methyl heptane dioate gives a mixture of 2 beta ketoester products. What are their structures and why is a mixture formed? So first thing I have to do is be able to draw this out. So heptane dioate. So I know it's ester. Hept is 7 carbons, so 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7. 3 methyl. 1, 2, 3 methyl. And it's diethyl dioate, so have the ethyl groups on the ends there. So if I count from one alpha position to the next, I have 1, 2, 3, 4, 5, 6. Okay, so again, I can form a 6-membered ring. At 1, I have my ester group. At 2, I have the methyl. So this 2, I'm just keeping track of where everything is attached in relation to my ring. Then attached to the 6, so I have my carbonyl there. Okay. But I start from this ester functionality on the left side here. What if I would have started from the one on the right side? I would have numbered it 1, 2, 3, 4, 5, 6. So again, a 6-membered ring. Again, 1 would have my ester on it. And this time it's attached to the 6 over here, so 6 is a carbonyl again. But this time my methyl group's at 4. Okay, so you can see I get 2 different products. So it says I get a mixture of 2 beta-keto ester products. Why are there structures and why is a mixture form? And why is a mixture form? It's because it's not symmetric. So I can take it off from this alpha position, form my product, or I can take off from this alpha position and form a product. That's why you get 2 different products. For some of these reactions, I'm going to keep the videos a little bit shorter, and so that way you may not have to watch them all in one setting, kind of take a break or something. So I'm going to finish it up here talking about Claissen condensations, and the next video will be a Michael reaction. See you then.